Greetings, folks. I'm Sachin Bhat from NTU Singapore, and I'll be presenting a paper titled NMRet, a Memory-Augmented Retrieval Framework for Large Language Models, developed in collaboration with Prof. Eric and Prof. Haibo. This work explores how we can make large language models reason over much longer context by integrating multiple complementary memory systems. Coming to the motivation, which is the context length bottleneck. Modern LLMs struggle with long contexts because attention costs grow quadratically. When we use chain of thought prompting or multi-step reasoning, the key value cache explodes in size. This slows inference and quickly hits memory limits. Prior approaches like linear attention or pruning improve efficiency but lose fidelity. Our question was, can we give LLMs an external memory that keeps important long-term knowledge without overflowing the context window? With that, we come to some concepts. So we took inspiration from cognitive science, where we know that humans use different memory types for abstraction, context, and working reasoning. Similarly, NMRet integrates three distinct modules. The first being Titan-style neural memory for abstract guidance, a vector store for concrete recent information, and a light thinker compressor that summarizes intermediate thoughts. These are coordinated through a multi-step reasoning loop. Now, let us look at the architecture diagram. Here, a user's query first retrieves document from the vector store. Then both the Titan's neural memory and the light thinker compressor participate in iterative reasoning. This system operates within a shared embedding space. So neural and vector memories communicate with each other through embeddings rather than raw text. These signals are then passed to the LLM, which then transforms the response into a user-friendly format. So coming to the Titan's neural memory wrapper. So this is based on the Titan's PyTorch neural memory package and learns to memorize at test time by maintaining an internal state, which is termed the neural mem state. So this wrapper manages the stateful model that learns from sequences even during inference. It updates step, encodes new embeddings, say, for example, the documents output or even the LLM's output, while retrieve produces an abstract guidance vector that influences the LLM's next thought. Essentially, it functions like a long-term continuously learning memory. Now, coming to the vector store and light thinker modules, the vector store keeps short-term factual memory, which are chunks of retrieved text or prior reasoning, so that we can recall exact facts. The light thinker compressor, on the other hand, is inspired by the light thinker paper from 2025 and asks the LLM to compress its own reasoning into a short summary and embedding. This prevents context window bloat while preserving continuity between reasoning steps. Now let's come to the multi-step retrieval loop. So this core engine here is this multi-step loop. Each iteration retrieves from the contextual and neural memories in parallel and then feeds them to the LLM. Optionally compresses the output and updates the memories. This iterative design lets the system refine context and internalize knowledge over time, something that standard RAG pipelines currently don't do. So coming to the experimental setup. So following were the data sets we used. The first being CoQA, which is a conversational question answering data set. AI Archive 2, which is a factual question answering data set for the archive papers for a few genres, being computational physics, computational biology are some of the examples. TextVQA, which is visual question answering. So here the metrics used are the Ragas metrics, which include answer relevancy, precision, faithfulness, recall, and context relevancy. The configuration used here our reasoning steps being one. We did not compress any intermediate information, and we updated the Titan's memory with only the document outputs. And then the embeddings used here were the clip embeddings of 512 dimensions. So this was done to keep a minimal configuration to isolate baseline behavior. So now let us look at the results. So the results here show that NMRet excels in domain-specific factual retrieval, especially on AI Archive 2, achieving almost perfect answer relevancy. On the other hand, CoQA and TextVQA, the context precision and faithfulness dropped because the system only had one reasoning step and no compression. Essentially, it could retrieve good answers, but not always ground them in complete supporting context. So this can also be seen here in the context precision, and other relevant results are also displayed here in this table. So coming to the actual limitations and future directions. So while promising, this is still an early prototype. The evaluation was limited and the compression was off. So we haven't yet realized the full potential of multi-step reasoning. Going forward, we plan to enable this iterative reasoning, use compressed LLM states for updates, and run larger scale benchmarks to see how memory augmented retrievers like NMRet can truly extend the thinking horizons of LLMs. So here are some of the resources. So the code used here is hosted on GitHub and is compatible with the orchestration frameworks of LangChain and LangGraph. So with that, we come to the end of this short presentation. Thank you for being a wonderful audience.